Philip Gonzalez is a Chilean physicist specializing in the study of planetary interiors through the study of the physics of materials under extreme pressure and temperature conditions. He earned his PhD in University of Chile and is currently a project scientist in the EPS department um, with working with Berkeley School. His notable publication includes studies on the metallic hydrogen and application to the cores of the giant planets. And his award include the fellowship for PhD study in the Chile, which is called Contested Fellowship, and postdoc fellowship at UC Berkeley, and two nominations in 2023 and 2021 from the APU to the editor citation for excellence in reference, recognizing him as an excellent reviewer for the journal review. And today's our pleasure to hear his talk from super-Earth cores to dissolving gas giant interiors. Let's welcome.
Well, thank you very much for that kind introduction. And I'm really honored to be here, the invited speaker today, because it's my first CIPS seminar after all these years working here at UC Berkeley. And I would like to take this chance to show you what I've been doing all these years, which has to do with what you're seeing right now on the screen, which is the very deep interior of planets and how we can use mineral physics from the atomic scale to infer properties that are actually relevant for planetary scale problems. So this is research that I've been doing with Berkeley Military in the Department of Earth and Planetary Science. And I want to first give you an overview of my research. So my research encompasses these three main areas. I mostly do high pressure physics, where I study transitions from solid-solid phase transitions, characterize equations of state and melting. And most of the time I use materials. I study materials that are relevant for planetary interiors that make up their composition. So the properties that I infer can inform models for super-Earth interiors on core mantle crystallization, partitioning, and phenomena like solubility and melting. And all this research sometimes intersects with this regime called warm dense matter, which is a really strange phase of matter where the temperatures are as high as a plasma, but the densities are also very high. So the atoms are not fully ionized. They are partially ionized, and they are very difficult to characterize. So this is very important if you want to study the envelopes of white dwarfs, for example. So the question behind this all is always, what can I do with first principle? What can first principles help me with to reveal important questions that appear in the planetary science realm? So to motivate this question, I want you to think about planetary formation in general. So how do planets form in a nutshell? You have a protoplanetary disk where there's dust around that sticks together, and then it agglomerates until it forms rocks. The rocks start accreting until they form larger bodies. Of course, I have skipped 1,000 steps in this process. It's a very complicated process that you in the audience very likely are dealing with. But in a nutshell, that's how a planet forms. And after a period of thousands of years, then you have created a large enough body that is enough to pull other small rocks through gravitational attraction. And the energy delivered in these impacts is so high that you end up with a completely molten planet. So that's what we call a magma ocean phase. So from a material science perspective, we ask questions about the thermodynamics of formation of planets. What's happening with the actual materials that make up these planets at the conditions that they are now? Because new pressures were formed at the interior, really higher temperatures that at the beginning are present. So the thermodynamics changes. So we wonder, how do these planets cool down? How do cores form and when? And is there an even rocky core? Did the planet differentiate? Or is the core molten? Do new phases of matter that appear at high pressures affect the evolution of the planet? And are there even magma oceans that are long-lived? All these questions have to do, in the end, with material science. So we have to know our materials in order to say something relevant about the planetary interior. And if we compare the models that have been done lately for the Earth and super-Earths, you can see that for Earth, we have 6,000 kilometers beneath our feet. And the pressure that you get at the very center of the Earth, like inside the inner core, is about 360 gigapascals. That's 3 megabar, 3 million times the atmospheric pressure. But if you go to a super Earth, we're not even halfway through the mantle when you already exceed the highest pressure at the Earth interior. So this means that the mantles of these super Earths may be subjected, the minerals that make the mantle, to pressures that we don't see on Earth, and the minerals undergo different phase transitions that just don't exist here on Earth. And we really need to do new experiments and new simulations to understand what happens with matter at these conditions. And if you can see here, the pressure at the core is 1,300 gigapascals. That's 10 million atmospheres when you just have entered the core. So what happens with the melting of materials at those insane pressures is something that we have to figure out before saying anything meaningful about these planets. So I don't have to tell you that more than 5,500 exoplanets have been discovered in the recent years, because it's you, the community, that discovers these planets, and I just get the mass and radii from these planets to perform my research and say something about the interior. But you might have heard too that they come in different categories, like gas giants that we have in our solar system, terrestrial planets. But it turns out that the most popular type of planets are the super-Earths and sub-Neptunes. And this is because they come in this bimodal distribution where people have discovered that there's a larger number of bodies that are around like 1.6, 1.3 Earth radii, and another group here around 2.4. And there's this radius gap or radius valley that they call it that separates these two classes of bodies. So we wonder, how is that these planets form? Why these bimodal distribution appears, and what are they actually made of? Does it mean that they are actually made of rocks versus the others that are more puffy with other volatiles? And one of the systems that have gained a lot of attention is the TRAPPIST-1 system, which is a system of 7 exoplanets that have such really interesting orbital resonances. They are all in a habitable zone, and they're almost like Earth in the sense of sizes and masses. And people are currently putting out models to understand what they are actually made of. Yeah, and they are analyzing how the atmosphere interacts with the interior. So, for example, in this work, they have studied how the energy fluxes and volatile fluxes of the atmosphere changes with pressure and temperature as you get deep down in the planet, and how that interacts with the interior, where you have trap of volatiles inside the melt that is deep down inside the planet, and how these processes that occur at the very deep interior of the planet can change and alter the atmosphere above. So all these questions are interesting to me, and that's how I perform my research. So I would like to show you today, divided in 4 main topics, a set of the projects I've been involved in. And I want to start talking about super-Earth and crystallizing iron cores. Then we will talk about Jupiter, then water worlds. And if we have time at the end, I will talk a little bit about this warm dense matter I told you at the beginning. So to start talking about the cores of super-Earth, I have to tell you about the history of the melting line of iron. And I want to start with this figure I made. So if you ask a material scientist the question of what is the melting temperature of pure iron at 330 gigapascals, there should be just one answer. But you can see over here that the answers are scattered all over the place. So the experiments are difficult. It's a very hard measurement because the pressures are really high, but also the temperatures are high. And you can see that the experiments here circled in red do not agree with each other. They are kind of in a range, and they have a very large error bars, about 400, 500 Kelvin. But also we don't agree between the theorists, because the way in which we do the simulations depend on a series of assumptions, like which is the structure that you assume that is melting for that pure iron, and what is the methodology that you actually utilize to calculate melting. What do you mean by melting temperature? It is not as easy as it seems, or just heating the material and wait until it melts. So it's a difficult question in the end. And I want to show you how are we currently measuring the melting temperatures at these extreme conditions. And this is the latest assessment of the melting curve of iron at super-Earth core conditions, which is an experiment done in Livermore, where they have these gigantic lasers that go through these tubes that are about like this big. And each of those lasers that you see there is just laser light. It's not water, but it looks like a pipe. And it's like about 200 lasers that are coordinated, pumped in energy such that they gain a lot of power, and they coordinated arrive at the same spot and that chamber that you see at the very end at the same time, and they flow to reach a really, really tiny chamber that is at the middle of the chamber that is about, I don't know, 3 people tall. And this chamber contains usually a fuel, because the goal of this experiment is mainly to do fusion by inertial confinement. And the experiment lasts just few billionths of a second. So in 10 billionths of a second, you have to take all the measurements and characterize these materials to reach for a very tiny fraction of time a really new state of matter. So in addition to doing these fusion experiments, we can also probe materials that are relevant for planetary science at these extreme conditions. So this is what they did at the National Ignition Facility here in Livermore. And what they did was send a shock into just pure iron that melted, and it looks more or less like this, a shock into the material. And then the shock molten iron was then compressed again with a ramp wave that allowed it to cross the melting curve, meaning that they were able to see the crystallization in situ in that very brief amount of time of iron from the liquid state to the solid state. So that's how they were able to place constraints on the melting line of iron. And they were, for the first time, able to measure the melting temperature of iron up to 1,000 gigapascals. That is 10 million atmospheres. So that's like the best constraint that we have from experiments of the melting line of iron. So why is this relevant for planetary evolution, in particular the evolution of the core? So if you think of the state of magma ocean that I showed you at the beginning, what is the initial state? A very hot planet where everything is molten. But with time, the planet cools down, and eventually, after billions of years, the whole thing will crystallize, right? Everything will freeze, and we will have a frozen core and a frozen mantle. What happens first and what happens last depends actually on the material properties, because you have to study how the adiabat of the planet interacts with the liquidus of the materials that the planet is made of. So this is how we study this phenomena. If you have an adiabat that is shallower than the liquidus, has a shallower slope, then you will see that the intersection between the two will occur at the highest pressures first, and the highest pressures occur at the very center of the planet, right? So as the planet is cooling down, the adiabat is going down, and then the intersection takes place at the highest pressures, which means you have a bottom-up crystallization. But to the contrary, if you have an adiabat like the mantle that looks like this, that is steeper than the liquidus of the mantle in that case, then you will see that as the adiabat goes down, the intersection will take place at the lowest pressures first, and lowest pressures are at the surface. So then you will have a case of top-down crystallization. So you have to understand this interplay in order to know how these planets crystallize. And you have to propose materials that these planets are made of in order to characterize their properties. So in the case of Earth, the mantle adiabat, very roughly, is something like this. It intersected the melting line of MgSio3, which is one of the most common minerals in the Earth's mantle. And it intersected at an intermediate pressure range, which means that the mantle, at least some studies show, started crystallizing from the center, not from either the bottom or the top. But then you realize that just because the melting of temperatures of silicates are higher, that means that the mantle crystallizes first and then the core, right? So which is what happens with the Earth. Remember that the Earth inner core, the solid one, has only about 1 billion years of existence. It did not exist for an entire history of the Earth. But that might not be the case for super-Earths. Who knows, right? So the way to read this plot is, again, to remember that the zero pressure means the surface. and that the core mantle boundary pressure highlighted in this vertical line is where the mantle and the core meet, right? So we're interested in what happens at a certain pressure, means we're interested in what happens at a certain region of the planet. So many experiments, like the one I showed you from shock experiments, and others from diamond anvil cell experiments, constrain this melting line at high pressures. They have to reach those high pressures and observe melting and crystallization. But for materials in the mantle, for the very, very high pressure regime, there are actually not many experiments available. And most of the estimates come from simulations. So one of the few experiments that has been done at the really extreme hundreds of gigapascal regime, the megabar regime, is this one by Ingwei Fei, where they shock compressed enstatite, which is a bridgemanite in this case, a high pressure polymorph, representative of the mantle, and they constrained just one point here when it intersected the melting line. And they drew melting line looks like this. Again, higher than the melting line of iron, no surprise, but we have a constraint at higher pressure. It's not just an extrapolation. But there are other experiments that have been performed at these extreme conditions that started exactly with the same material, but with a different phase of the material, and placed a constraint over here at lower pressures. And according to this experiment, now this is the melting line that they obtained, which is considerably lower. And it has really important implications for planetary evolution, because if you have a melting line of silicates below the melting line of iron, again, that will mean that the core starts crystallizing before the mantle does, which is completely reversed than what happens for the Earth. And whether that actually happens depends on whether we can confirm these experiments. Okay, so is it possible that silicates have lower melting temperatures of iron in some regime, because that has planetary implications? And is it possible that then the core crystallizes first? And in order to constrain this question, I will address the first part, which is the melting line of iron. Do we have the right melting line of iron? How does it coincide with the experiments, the latest experiments that I showed you? And I want to tell you the results before I showed you how I calculated them, and which are basically this blue line here. This blue line is basically the melting line that I calculated for pure iron at extreme conditions, up to 5,000 gigapascals. And I want to give you the takeaways before we start, is that our predictions first agree with experiments, the ones I showed you earlier, and that implies that super-Earths start crystallizing from the center, so in a bottom-up scenario, and that all the cores of super-Earths might be frozen. So how did we do this? What we basically do is calculate energies. And we have to calculate free energies. I won't delve into details here. You can ask me later if you're interested. But the main quantity we're after is this Gibbs free energy. What is the Gibbs free energy of solid iron and of liquid iron at different pressures and temperatures? And all we want to investigate here is where are the conditions where the Gibbs free energy of the liquid is the same as the Gibbs free energy of the solid, because that's the definition in thermodynamics of the melting point, right? So we ran a series of calculations and we verify where these two energies meet, and that's how I obtained these blue marbles that you can see here, which are all melting points that they all make a melting line. So the first thing that you can see here is that it agrees very nicely with the experiments that I showed you at the beginning, with the error bars in red, right? And that the first thing that this shows you is the predictive power of our simulations. Without having any access to the experiment and doing completely independent, we're predicting the same measurements that they did at the laboratory, even at these extreme conditions. But since I can crank the pressure as much as I want, I can go to even higher pressures. And that's how I was able to get to 5,000 gigapascals and extend this melting line to regions that have not been explored before. So in addition to the melting line, since we're calculating these Gibbs free energies contain entropy that I can also calculate. And since I have the entropy at different pressure and temperature conditions, I can calculate planetary adiabats, which are lines of constant entropy that you see here in red. And as you can see, the The adiabats are shallower than the melting line, which again implies bottom-up crystallization, starts crystallizing from the highest pressures first, the intersection. And they represent convective regions of the planet, not like the mantle. In this case, is the core that is convecting, and it's represented by each of these planetary adiabats. So we conclude that the super-Earths that are in this regime of really, really high pressures crystallize the same way as in the Earth from bottom-up crystallization. But we still haven't built a model for this. So that's what we wanted to do next. What can I do with these properties that I inferred to get a model for a super-Earth that tell me about the boundaries of temperatures that they can be subjected to? So we built a planetary interior model that maybe a few of you have seen before. You just have to assume a few things. For example, a differentiated planet when the iron is at the center and you have a layer of silicates. And you have to solve a few equations, like an equation for the mass, which is literally the mass enclosed in a spherical shell of density rho. And you have to balance the pressure with the gravity, basically to prevent your planet from imploding, and an equation of state, right? And the equation of state is the relationship between pressure, density, and temperature that is unique for every material. So every material that you put in your model needs to have this characterization. And where do you have this from? From experiments or the simulations that I perform, right? So once you have all these three equations, you solve them. It's a set of three coupled differential equations. And you obtain plots like this that you can see in the literature, where you can see that the density of the planet from the surface increases as you go down, deep down in the planet. Then you have a density jump when you cross to the core that has much higher density because it's iron. And you find the highest density and pressure at the very center of the planet. But these models have certain free parameters. For example, what is the fraction of iron that you put at the center? So if, for example, in this case, I'm focusing on a 5 Earth masses exoplanet, what happens if I keep the mass, 5 Earth masses, but I change the core mass fraction? I can go all the way from a almost fully iron-made planet with a thin layer of silicates to something that is like Earth, like 0.3 or 0.2 by fraction by mass of iron in the core, and that will change the radius of the planet. So if you put more iron, the planet is smaller. If you put less iron, the planet is bigger, but for the same mass. And that will have unique pressures at the center and at the core mantle boundary, right? This region where the core and the mantle meet. And that will place in the phase diagram of iron the pressures I have to look at to understand where crystallization starts. So in this case, if we want to focus on planets that are 1.6 Earth radii, which again has to do with this radius gap, we consider that planets are rocky, like about that size, because larger planets are likely to be contain like substantial atmospheres. And we have these pressures that I will look in the phase diagram of iron. So comparing with previous models that have been trying to address this question, you will see in the literature that very low temperatures have been proposed for the average temperature at the interior in the order of 5,000 Kelvin. But if you look at this diagram that I have obtained for a 5 Earth masses exoplanet, the pressure at the very center is about 2,000 gigapascals. So that means that you need to exceed temperatures beyond 15,000 Kelvin to have liquid iron, while the pressure at the core mantle boundary for such a planet will have pressures of about like 700 gigapascals, which means that you need temperatures beyond, say, like 9,000 Kelvin, right? So according to our models, when the average temperature in the entire core drops below 12,500 Kelvin, then you already start crystallizing an inner core. And when the temperature has dropped below 10,600, then you have completely frozen the entire core because the pressures and temperatures are not compatible with liquid iron anymore. So that would eventually mean that these simulations predict that super-Earths might have frozen cores entirely unless you're able to maintain a temperature that's beyond 10,000 Kelvin. Now, is this temperature too much or too little? Well, that depends on how much energy was delivered on accretion and whether models are compatible with such a high temperature in the beginning. But I guess that this will challenge at least many models that have been put out where they suggest that much lower temperatures. And I am happy to see that a few colleagues have already been using our model to characterize new types of problems. For example, this that these most high density exoplanets are unlikely to be remnants of giant planet cores. So, which was a really interesting study that was fed by this equation of state of iron that we built. So this is more or less how I view the field and this type of things I work in. And now I want to switch gears from rocky super Earths to tell you something about Jupiter, which actually goes back to my very first project that I ever had in planetary science. And this is something to do with the structure of Jupiter itself and how we believed it was at the beginning. Remember how planetary formation works? You have to accrete a lot of rocks to create a large body. In the case of Jupiter, we believe it was a 20 Earth masses body that grew to have enough gravitational pull to attract the gases around it. So after the planet was formed, there was a lot of chemistry that went around, and it left an upper layer of hydrogen-helium mixture, and below this one is a layer of helium rain, and only below those layers, there's a region of an ocean, actually, of metallic hydrogen, which is actually what makes the entire magnetic field of Jupiter. But since this metallic hydrogen was formed later in the formation of Jupiter, then is it possible that at the conditions that this core is now, which is about 40 megabar, and temperatures of thousands of Kelvin, is it possible that the metallic hydrogen can dissolve the core, right? So how do we even address this if we don't have any experiments that can even synthesize metallic hydrogen and play around with rocks? We have to do chemistry from first principles. So in order to address this question, we basically went to the equations of thermodynamics, and we chose a material, as usual. In this case, it was silica, because we believe it's one of the common rocks to be found there in the core of Jupiter. And we were focused on the following chemical reaction. Can N atoms of hydrogen in the metallic form interact with 1 unit of silica to form a dissolved system of hydrogen and silica? So what I have in mind basically is that silica is surrounded by a lot of these hydrogen atoms in the metallic phase, and they basically dissolve the rock. And then you have to compute what are the energy differences between the original state and the final state. So basically the free energy of solvation. The first term in this equation is just the Gibbs free energy of this dissolved system. And the second term is just the energy of the parts, hydrogen and silica. And the only thing I want you to take from this is that if this thing is negative, the thing dissolves. Okay? So I just want to compute this Gibbs free energy difference between these two systems. And whenever it's negative, it means that the dissolution of silica is favored energetically. So this is what we found. Below here, all the values of delta G are positive, and above here, all the values of delta G are negative, which means it dissolves. So at these temperatures and pressures that you see in this plot are all in the range where the Jupiter core mantle boundary conditions are and the Saturn core mantle conditions are. So it means that at the pressures and temperatures of the cores of these planets, the dissolution of this material, silica, is favored. And we did it not only with silica in our group, all the members of our group have tried all the materials like magnesium oxide, iron, and water, and all these materials become dissolved by the metallic hydrogen. So it means that at the interior of Jupiter, metallic hydrogen is a pretty good solvent of rocks. And this has changed our picture of how we understand Jupiter, because now, rather than having a compact core in the center, that doesn't mean that it's necessarily solid, but it's a compact core, it's actually not compact at all. And it's a dissolved core that can extend even to the half of the radius of the planet. So the current models that have been put out for Jupiter consider a dilute core that extends for a wide distance, and above it is the metallic hydrogen in more pure form. But now you say this is conclusions that we draw from material science. So how can we actually prove that this is happening in Jupiter, right? Well, it turns out that we have a spacecraft going around Jupiter, the Juno mission, and Burkhardt with collaborators of the Juno team using the gravitational moments that they measure, which is nothing than but an integral of the energy, the density profile of the planet. They concluded that it's inevitable to have a dilute core in Jupiter. So all the measurements of the gravity field of Jupiter imply that you have to have a smooth density profile. It cannot be sharp, indicating a compact core. So we're really happy that this basically is like a test of our predictions of years ago, where we predicted that the core would be dissolving. So is in the line of this conclusions. Now I want to switch gears again and tell you about another category of planet, which is what we call the water worlds. And you can understand them basically as a subcategory of Sub-Neptunes, where we believe that there's considerable amount of water in these planets. So this study was led by Tanya Kovacevic, a student in our group, where I participated. And basically, what we were after was the following. Consider the types of planets that the density is so low that it cannot be explained by a rocky mantle with an iron core. Otherwise, it would be too dense. But it doesn't have a substantial atmosphere as either. So there must be a significant amount of water, maybe 50% of the weight of the planet, in just water ice. And again, related to this radius gap, there must be an interaction between the rock and the ice that is not as we usually think that water interacts with rocks at ambient conditions, because yeah, we have the Super-Earths and Sub-Neptunes, and we want to understand the interaction with superionic water, because water at these extreme pressure is not the same molecular water that you know. It goes into this superionic phase where you have the oxygen atoms that you can see in this lattice here staying still, like vibrating around the lattice positions. But the hydrogen atoms are flowing in this lattice like a liquid. So it has characteristics of both states of matter, a solid and a liquid. So whatever interaction that rocks have with superionic water is very non-intuitive. And the concept of water molecule does not exist at these conditions. So we started by running some particle hydrodynamic simulations, and we collided some water worlds to guess more or less what are the pressures and temperatures you end up in an event of a collision of when you form these planets. But the problem with these types of simulations is that they do not consider chemistry. Basically, if a particle, say a blue particle that is water, will always be water. It cannot change or interact with any other particle chemically to form something new. So that's precisely what we wanted to address. So given the range of pressures and temperatures we had, we literally exposed a slab of water to a slab of rock subject to different pressures and temperatures. And at the highest pressures and the highest temperatures, that we observed, this is what came out of the simulations. You will see that the hydrogen atoms here in white will flow really rapidly through the entire system. And this is not fast at all. So the video is a little bit frozen, but yeah, well, there's working. You can see that it's completely molten, but it also merges all the atoms in a homogeneous way. Basically, when the system melts entirely, they do not remain as separate liquids that are phase separated. They form a new phase of matter where everything is completely mixed. And that happens at the highest temperatures above this red line. And of course, at the lowest temperatures we simulated, nothing happened. You have like happy solid water in front of solid rock. Then if you increase the temperature, like given by these crosses here, you access the superionic regime of water that is on top of the rock. but they don't interact. It means it doesn't dissolve the rock. Then at even higher temperatures, the water is completely liquid beyond the superionic phase, and the rock remains solid. And again, they do not interact. It doesn't dissolve the rock. And it's only when you go above the temperatures of the melting line of MgSiO3, in this case, that you access this regime where both are molten and they start mixing readily. So this has changed basically the picture that we have for the interior of these eventual water worlds, where rather than really nicely separated layers of water and silicates, we think that there's like a gradient of composition, which makes the problem even more difficult to track because it will alter convection in these planets and the heat transport. But it's important to consider if you have want to have a realistic picture of what's happening inside of these planets and how they cool down. Okay, and I want to tell you a little bit about a project that actually Kyla, this student in our group, presented a year ago here in a CIPS seminar, which is a very cool project where she discovered this new phase that we coined double superionicity. And basically what Kyla did was to focus on Uranus and Neptune and the composition of these planets. It has been suggested that it has a lot of this superionic water, but it also has hydrocarbons and things mixed up with nitrogen. So the thing is that at the extreme pressures of these planetary interiors, you form new materials in the solid phase. Even the temperatures are high, new compounds are formed. So in the quaternary diagram of different formations of phases, you can find new materials like HCNO, like a completely happy solid. And what Kyla did was analyze basically 10 of these materials and expose them to different pressures and temperatures to see what would happen with them. And what she observed is that not only the superionic phase appeared where the hydrogens are flowing like a liquid, but a second species, in this case nitrogen, was also flowing like a liquid in the lattice of still stable oxygen atoms. So this was a new phase of matter for hydrocarbons that have never been reported before. And that's why it made it through science communications. And it's important for Uranus and Neptune in particular, because if you have these materials with mobile atoms, it means that you have mobile charges. And if you have mobile charges, you have currents that can eventually generate magnetic fields, and you have to connect them with the observed magnetic fields of Uranus and Neptune. So if you want to have a full picture of the planet. Okay, and since we do have a little bit of time, I will tell you a little bit of this warm dense matter that I told you at the beginning, which again is this phase of matter that appears when you have really, really high densities and really, really high temperatures at the same time. So it encompasses the imploding capsules in the Livermore experiments. You can see that there are densities that can be higher than Jupiter's core, but are particularly relevant for white dwarf envelopes. So what happens with matters at these extremes is generally characterized by shocks that I told you a little bit at the beginning about. We can reproduce these shocks with our simulations, where we basically build a gigantic equation of state, exploring many densities and temperatures, and monitor the dependence of the pressure and energy of a given material as a function of temperature, and see how it changes from a few thousand Kelvin up to a billion Kelvin. And we build a consistent equation of state that is important to report properties and build this ranking. With these ranking Hugoniot equations, we build this shock curve that I showed you earlier, which characterizes the locus of points of shock conditions in an experiment. And we have been successful in replicating experiments with this technique. You can see here our black line for MgO matches really nicely with shock experiments of magnesium oxide here. The same for MgSiO3, where we have a pretty good agreement with the experiments, showing you again the predictive power of our simulations. So we have put together an entire software called First Principle Equation of State, FPOS, that anyone can download and use to create new equations of state under this approximation of linear mixing that allows us to create new equations of state under this approximation, and has been successful, for example, replicating the shock Hugoniot curve of carbon dioxide, which again is interesting to analyze the envelopes of white dwarfs, where you have a different stoichiometries that you can vary with this code in a very simple manner. And if you're interested, you can reach out to me to tell you more about it. So with that, I would like to finish and acknowledge the centers have been part of the DOE and my collaborators. And I will just leave my conclusions on the screen and happy to take any questions. Thank you.
For the iron, do you include all the other elements?
Other elements in what sense? Other chemical elements?
All the other.
What do you mean, electrons, protons, or you mean